Hello, this is Mr. Collier, and today we're doing some more exponential applications. So in the first example, Sally's salary increases 5% per year. So her salary is modeled by this equation, k times 1.05 to the power of n, where n is the number of years. Okay, so you always get a situation if something's increasing 5% per year, then you multiply by 1.05 to the power of n. Okay, so the value of k, find the value of k if her starting salary is 15,000. Well, this number here, k, this is always going to be the initial amount. And we can see that algebraically, if her starting salary is 15,000, then the number of years is going to be 0. So her starting salary is 15,000. That equals k times 1.05 to the power of 0, because that's the number of years. And anything to the power of 0 is 1, so you're just going to have k equals 15,000. So her starting salary is 15,000, which equals k. In the next example, find the amount of money to the nearest euro, don't forget to round correctly here, that she is making after 5 years. So after 5 years, that's just n equals 5. So we have s equals, now we're going to have 15,000 times 1.05 to the power of 5. Alright, so we're going to work that out with a calculator. Okay, so 15,000 times 1.05 to the power of 5 gives us, and remember to round to the nearest euro, 19,144. So that's 19,144 euro. Okay, the number of years she must work to earn a salary over 25,000. Okay, so to find the number of years she must work to earn a salary over 25,000, I'm going to type in the equation into the calculator, then go to table. So I'm going to go to 15,000. I'm going to type in 15,000 times 1.05 to the power of 5, or sorry, x in this case. So we can graph it, or we can go to table, second function table. There's all my values. I'm going to find when the first year is that she gets more than 25,000. So that is year 11, so after 11 years. Okay, so after 11 years, she earns more than 25,000 euro. Okay, next example. An experiment, researchers found that the culture of bacteria increases with this formula, where n is the number of bacteria present and h is the number of hours since the experiment began. Use this formula to calculate the number of bacteria present at the start of the experiment. So again, that's going to be h equals 0, the time is 0. So at the start of the experiment, we have n equals 20 times 5 to the power of 0. That equals 1, so it's just 20 is the initial amount of bacteria. Number of bacteria after 5 hours, well, that's going to be 20 times 5 to the power of 5. So let's do that on the calculator. 20 times 5 to the power of 5. And we get 62,500. Okay, the number of hours it would take for the number of bacteria to reach 12,500. Okay, we can use our table. Actually, let's type in the function first, which is 20 times 5 to the power of x, and we go to second function table, and we're looking for Now let's see my function again. Did I make a mistake? No, 20 times 5 to the power of x. So these numbers should be getting larger. Actually, those numbers there are too large for the calculator to display. So when does it first reach 25,000? That would be after 4 years, or 4 hours, sorry. So after 4 hours. The exact number of hours it would take for the number of bacteria to reach 100,000. Okay, so this is exact number of hours it would take for that to reach 100,000. So we can't really use our table because we want the exact answer. So maybe it'll be like 4.32 hours or something. Your table won't be able to get you that. So we need to solve it graphically. And what you do is you're going to graph y equals 100,000, okay, along with your function, and find the point of intersection. Alright, so we're going to do that. We're going to graph, along with our function, we're also going to graph y equals 100,000. 1, 2, 3, 4, 5, that's 100,000. So we graph that, and we're going to need to go up to 100,000 in the window. So maybe I'll change that now. Our y max must go up to 100,000, at least 100,000. I'm going to go up to 110,000. It's a little bit bigger. And the x values, I don't think they have to be too large because it looks like it's growing very quickly. This could even be 10 maybe. Let's see what happens. If we can see the point of intersection, then we picked a good window. Then we can see the point of intersection, so that's good. We're going to find it now by going to second function trace. And we'll go down to intersect is number 5. And I'm on the first curve, press enter. Second curve, press enter. I'll go towards a guess. Looks like they meet about there. And so you can see the point of intersection is 5. The x value is 5.29. So after 5.29 hours. 5.29 hours. The number of bacteria reach 100,000. Okay, now we're going to look at an example of exponential decay where the a value, basically the base of the exponent is less than 1, and you're going to have a decreasing function. Okay, also known as exponential decay, like with the half-life of radioactive elements like iodine-131. So the half-life is 8 days. So if you have 320 milligrams of iodine-131, then after 8 days, you'll get 160. After another 8 days, you'll get 80. And after another 8 days, you'll get 40, and so on. Alright, so here's the formula for calculating the amount of iodine-131, where n is the number of 8-day periods. That's a little bit confusing, so we can also write this as t equals 320 times half to the power of n divided by 8 if you want n to be equal to the number of days. Alright, so we can also use that formula. So I'm going to use that to find out how much is left after 216 days. So I'm going to use my GDC, but I'm going to type in the equation I'm going to use first. So it's going to be 320 times half to the power of 216 divided by 8. And let's do that on the calculator. We're going to get, so I'm going to type that in, 320 times half, now I can do 0.5, the power of 216 divided by 8. And oh, I get a very tiny number on your calculator. That's in exponential notation, so I could write this as 2.38 times 10 to the power negative 6. 2.38 times 10 to the power negative 6 if you're using scientific notation. So we can also write this number as, we'll just move the decimal place 6 places, so 0.0000238. 1, 2, 3, 4, 5, 6. So it's the same thing. So it's a very small amount after 216 days. After how many days will there be 1.25 milligrams left? So to do that, we could use a table. If we want to get the most exact answer, we're going to graph y equals 1.25 and then find the intersection using GDC. So let's do that. Let's graph. So we need to graph 320 times half to the power of x divided by 8. Alright, and let's graph y equals 1.25. Alright, now our window. We have to figure out what our window is going to be. So the initial amount is 320 for the y values, and they're going to go down to close to 0. So for the window, I believe we need y min, negative 10 is fine. The y max should be about 320 or maybe 350. So a little bit more than that. The x values, well, we start off with number of days is 0. How many days? Now this is going pretty quickly. It's going down pretty quickly. Maybe we need 10 or just 20 or so. Okay, I'm just kind of guessing, and I'm going to graph. And, oops, I forgot to also graph. Oh, I did graph the other one. Y equals 1.25. So let's see, does that pop up? Where's y equals 1.25? Let me check my window again. Okay. That's good. I think it's so... Aha. It's so close to the x-axis you can't even see it. So maybe I need to not worry about this part up here on the graph. Maybe I need to make my y max a lot smaller because I only need to see up to 1.25. So maybe I'll go to 10 here. Let's see what happens when I do that. Okay, now I can see y equals 1.25. Can I see the point of intersection with the exponential? No, I think I need to go further to the right. So if I go further to the right, I need to increase my x max. So maybe 50. Let me try 50. Okay, there I go. I can almost see it. I need a little bit more. I'll go up to 100. And now I can see the point of intersection. So I go to second function, calc here, and go to intersect as number 5. Press enter on the first curve, press enter on the second one. My guess is pretty close to where they intersect. And I get x equals 64. Okay, so after 64 days, there will be 1.25 left. So after 64 days, there will be 1.25 milligrams left. Okay, so one last example. Value y of Johnny's car x years after it was purchased is given by this formula. Okay, so this looks like this is less than 1, so this is dk. It's going to be decreasing function. Alright, oh yeah, that's the first question. Is this an example of exponential decay or exponential growth? It's decay because a is less than 1 is greater than 0. It's between 1 and 0, so it's going to be a decay, which makes sense. The car's value usually decreases after it's purchased. How much did Johnny pay for the car? Well, you can get the initial amount by putting in x as 0. Right, so this, anything to the power of 0 is 1, so the initial amount is $21,000, I guess. It doesn't say in the question. Alright, so that's the initial amount. How much will the car be worth after 8 years? We we put in 8 for the exponent. Do that on the calculator. Okay. So 21,000 times 0.85 to the power of 8 equals, so I guess we'll round off to the nearest dollar. It doesn't say here. So $5,722. $5,722. Or euro, I guess it is euro. In how many years will the car be worth less than 1,000? So we don't need an exact number here. So we can use our table actually to do this. So I'm going to type in the function in the calculator and use the table. So it's 21,000 times 0.85 to the power of x, and I'm going to go second function, table, and find out after how many years the cars were less than 1,000. So I'll scroll down until I see a number that's less than 1,000. Okay, and that will be after 19 years. So after 19 years, the car is worth less than 1,000 euros.